It was the early 1990s. A man named Vito Barucchi was diving the river systems of the American Southeast, searching the murky sediment for fossilized shark teeth. Most people knew these rivers occasionally gave up relics from an ancient inland sea. Small teeth, common species, nothing remarkable. But Barucchi kept pulling up something different. Teeth that were broader, heavier, serrated along both edges. Some of them nearly as wide as his outstretched hand. And they weren't accidents. They kept appearing, again and again, in different rivers, different depths, always the same unmistakable shape. Over time, he collected dozens, then hundreds, and eventually he did something no one had done at that scale before. Using a modern great white shark's jaw as a structural guide, he began assembling the fossil teeth into a complete reconstruction. Not an illustration, not a model. An actual jaw, built entirely from real specimens. The result was large enough for a grown adult to walk through. And standing inside it, the question was no longer whether this animal had existed. The question was, what exactly had it been? For most of recorded history, the ocean has operated on its own terms. You can stand at the edge of the water on a calm day, look out at the surface, and feel like you understand it. But drop a few meters below that surface and visibility collapses. Drop a few more, and you are effectively blind. And in that kind of environment, where you cannot see, cannot hear, cannot measure, scale becomes meaningless. A great white shark reaches roughly 6 meters in length, around 20 feet. That alone is enough to change the way people think about the water. Enough to keep swimmers close to shore. Enough to make open ocean feel like a different world entirely. Now take that and multiply it by 3. Estimates for Megalodon's maximum body length range from 15 to 20 meters, 50 to 65 feet. A 2025 study analyzing fossilized vertebral columns pushed the upper ceiling to around 24 meters, close to 80 feet. That is not simply a larger version of a great white. At that scale, the animal operates by completely different rules. Its metabolism changes, its hunting strategy changes, its relationship to everything else in the ocean changes. But here is the fundamental problem with Megalodon. We know almost nothing about what it actually looked like. And the reason for that comes down to a single biological quirk that separates sharks from nearly every other large predator that has ever lived. Sharks have no bones. Not just partially. Their entire internal skeleton, every strut, every joint, every structural element that holds the body together, is made of cartilage. The same flexible, lightweight material found in the tip of a human nose. It is an evolutionary strategy that goes back hundreds of millions of years, and for most purposes it worked brilliantly. Cartilage is lighter than bone, which helps a large body stay buoyant without expending constant energy. It absorbs mechanical stress during high-force movements without fracturing. But cartilage has one catastrophic flaw as far as the fossil record is concerned. It does not preserve. When a shark dies and descends to the seafloor, the soft tissue disappears within weeks. Muscle, fat, organs, gone. But then the cartilage follows. The vertebral column, the jaws, the fin supports, all of it decomposes. What remains, what survives the millions of years between a shark's death and a diver's hand closing around something in the sediment, is only what was hard enough to resist the process entirely: the teeth. And here is where the arithmetic becomes extraordinary. A shark does not carry a single fixed set of teeth. It grows them in rotating rows throughout its entire life, constantly replacing old teeth with new ones, shedding them the way trees shed leaves. Over the full span of a megalodon's life, paleontologists estimate the animal produced somewhere in the range of 40,000 individual teeth. Everywhere it traveled, across every ocean it ever crossed, it left this trail behind. Teeth sinking into sediment, slowly replaced by minerals over geologic time, now scattered across ocean floors around the world, waiting to be found. That is why we have so many teeth and almost nothing else. And it is also why reconstructing the animal requires a kind of detective work that goes far beyond simply finding fossils. Paleontologists working on Megalodon use three primary sources of information. The first is tooth geometry. By comparing the proportions of Megalodon's teeth, their height, their root width, their curvature, against those of living shark species with known body lengths, researchers can work backward to estimate overall size. It is not a perfect method, but across hundreds of specimens from multiple ocean locations, the numbers converge into a consistent range. The second source is jaw reconstruction. The arrangement of teeth along a jaw tells researchers about the width of the mouth, which in turn reveals something about the size of the prey it was designed to handle. And the third source, in some ways the most visceral, is what Megalodon left behind on its prey. Fossilized whale bones from this period carry marks, and not scratches. Deep, parallel gouges cut through dense bone, spaced in a pattern that matches Megalodon's tooth geometry precisely. These are not incidental. They are the traces of a feeding event. And what they reveal is not a predator that merely grazed or scavenged. The impact fractures found on fossilized rib cages suggest an animal targeting the structural core of large prey directly, biting through the chest, not around it. The bite force required to produce those marks has been estimated at approximately 180,000 newtons. To give that number some meaning, a great white shark bites with roughly 18,000 newtons, already enough to cut cleanly through bone. Megalodon's bite was 10 times stronger. The closest everyday equivalent would be the pressure of 3 full-grown African elephants concentrated onto a single point. That force was not simply a byproduct of being large. It was a precision instrument. Megalodon's teeth were serrated along both edges, the geometry optimized specifically for cutting through dense, resistant material as efficiently as possible. This was an animal that had evolved over millions of years, not just to hunt large prey but to disable it as fast as physically possible, which makes sense once you understand why speed of kill mattered so much. Unlike most modern sharks, Megalodon appears to have been endothermic, capable of maintaining a body temperature substantially higher than the surrounding water. This is the same metabolic strategy used by the great white shark today, and it confers a significant advantage. Faster muscle response, greater sustained power, the ability to operate in cooler water. But it comes with a price. Warm-blooded predators burn through energy at a rate cold-blooded animals simply do not. Estimates suggest that to sustain its body at operating temperature, Megalodon needed to consume approximately 100,000 calories every single day, roughly 50 times what an adult human burns in the same period. Think about what that demands of an animal. Every day without a successful hunt is a day drawing down reserves. Every failed attack, every whale that escapes, every prey animal that outmaneuvers the strike carries a real physiological cost. For an animal this large, in an ocean that was always changing, there was almost no margin for sustained failure. This single fact, that Megalodon's body demanded constant, massive fuel inputs, becomes the thread that eventually unravels the entire story of its extinction. But we will get to that. First, there is a persistent misconception worth addressing. Not what you think. Most people assume the great white shark is Megalodon's direct descendant, that if you trace the great white's lineage far enough back, you eventually arrive at Megalodon as an ancestor. That is not what happened. Megalodon and the great white are approximately as closely related as a dog and a cat, They share a distant common ancestor, an early shark lineage that diverged into two entirely separate families tens of millions of years ago. Megalodon belonged to a group called the Odontodontidae, defined by enormous, broad-based teeth and extreme body size. The great white belongs to the Lamnidae, a separate family that includes mako sharks and salmon sharks, built along completely different lines. These two lineages, when they diverged, effectively made different evolutionary bets. The Odontodontidae scaled up. They became progressively larger across successive generations, eventually producing the biggest shark and one of the biggest predatory animals that has ever lived. The entire strategy was built on mass, on force, on the ability to take on the largest available prey. The Lamnidae went the other direction. They stayed relatively compact but became faster, more agile, and thermally efficient in a wider range of water conditions. At the time, both strategies were made, both worked. The ocean was warm, productive, and full of large prey that rewarded the kind of brute force predation Megalodon had perfected. But one of those bets had a longer shelf life than the other. Megalodon first appears in the fossil record approximately 23 million years ago. The ocean it was born into was fundamentally different from the one we know. Sea temperatures were warmer. Shallow coastal seas extended over large portions of what are now continental land masses. And critically, the dominant large marine mammals of that period were not the filter-feeding giants of today. Early whales were mostly toothed animals, quick-moving, moderate in size, distributed through relatively accessible coastal waters. Megalodon did not simply occupy the top of this system. It shaped it. An apex predator at this scale influences everything below it in the food chain. It determines which prey species thrive and which are kept in check. It drives evolutionary pressure on every animal within its range. For roughly 13 million years, Megalodon held that position in the world's oceans. 13 million years. The entire evolutionary history of the human genus, from our earliest identifiable ancestors to today, spans approximately 3 million years. Megalodon as a species persisted through more than 4 times that span. It was not an evolutionary experiment that briefly flickered and failed. It was one of the most durable apex predators in the entire history of life on this planet. Around 5 to 6 million years ago, a combination of factors began converging. Not a single catastrophe, but a slow tightening, each element compounding the others until the total became insurmountable. The first shift was climatic. Global temperatures began to drop, and as they dropped, the oceans responded. The warm, shallow coastal seas that had persisted for millions of years started retreating. The productive near-shore environments where Megalodon's primary prey had been concentrated began to shrink. At the same time, something was happening to the whales. Faced with changing food availability and increasing competition, a group of early toothed whales underwent one of the most consequential evolutionary transitions in marine history. They abandoned individual predation. Instead of pursuing single prey animals, they evolved baleen, long, fibrous plates that function as biological filters. Now, rather than hunting, they could move open-mouthed through vast concentrations of krill and small fish, straining enormous quantities of food with minimal effort. The logic behind this shift is mathematically elegant. Every step up a food chain represents an energy loss. Roughly 90% of the energy at each level is burned before it reaches the next. A seal must eat many fish. Those fish must eat smaller fish. By the time that energy reaches the seal, most of it has dissipated. The early baleen whales effectively bypassed the entire chain. They fed directly at the base, at the level of maximum energy density. More food, less effort. No ceiling on body size. And so they grew. With essentially unlimited nutrition at the base of the food chain and no predator capable of threatening adults, there was no biological incentive to stay small. Over millions of years, these animals became progressively larger, generation by generation. But here is what that transformation meant for Megalodon. The prey it had relied on, moderate-sized, warm water, relatively accessible toothed whales, was vanishing. Some species were disappearing entirely as habitat contracted. Others were in the process of becoming something Megalodon could no longer effectively hunt. An animal in the early stages of growing to 60 feet, protected by sheer mass, moving through open deep water, that is a fundamentally different target than the prey Megalodon's entire body plan had been optimized to handle. And now, something else was happening simultaneously in that same ocean. While Megalodon's prey base was eroding, the ancestors of the great white shark were quietly becoming something more formidable, built for colder, deeper water, faster and more maneuverable at smaller body sizes, capable of pursuing agile prey through environments a 15-meter shark could not efficiently navigate, and critically, able to target early baleen whales while those animals were still small enough to be vulnerable, before millions of years of unchecked growth had placed them beyond the reach of any predator. What was occurring, in effect, was a gradual handover of ecological function. The prey that had sustained Megalodon was either disappearing or transforming into something beyond its reach. And into that opening, the ancestors of the great white stepped quietly and efficiently, taking smaller pieces of a shifting ocean in ways that a massive, high-calorie-burning predator simply could not replicate. This is why some researchers describe the great white lineage as an indirect driver of Megalodon's extinction, not because they competed directly for the same prey on the same day. There is no evidence of direct confrontation. But Megalodon was built for an ocean that was fading. The great white lineage was adapting to the one taking its place. And for an animal burning through 100,000 calories a day, there was no way to wait out that transition. Still out there? There is one question that follows Megalodon wherever the subject is raised. Is it still alive? It is worth taking seriously, because the instinct behind it is not completely unreasonable. In 1938, a fishing trawler working off the South African coast pulled up a fish that scientists had classified as extinct, a coelacanth, alive and undiscovered, for 66 million years. So the logic follows. If a fish could remain hidden in the deep ocean for that long, why not a 60-foot shark? Here's the answer. Megalodon shed approximately 40,000 teeth over its lifetime. In every ocean it ever traveled through, it left them behind. They are found on seafloors across the globe, and the most recent Megalodon tooth ever dated was deposited 3.6 million years ago. Not 1 million, not recently. Not from an ocean floor that could suggest a lingering population. 3.6 million years ago. Modern whales, which would represent the obvious prey for an animal of this size, show no bite marks consistent with Megalodon. None. In the entire global record of modern whale bones and strandings, there is no trace of an attack pattern that matches its tooth geometry. And the coelacanth survived because it lives in deep underwater caves, barely moves, and requires almost no caloric input to maintain itself. It is metabolically the opposite of an active apex predator. Megalodon, an endothermic animal requiring 100,000 calories a day, operating at the surface layers of the ocean where its prey lived, that animal cannot hide. There is nowhere to hide that would not leave evidence. It is gone. It has been gone for nearly 4 million years, but its absence changed everything that came after it. For as long as Megalodon existed, baleen whales had a hard ceiling. Juveniles had to remain fast and difficult to track just to survive long enough to reach adulthood. The evolutionary pressure Megalodon exerted kept the entire system calibrated to a certain scale. The moment that pressure lifted, the moment Megalodon was gone, the ceiling disappeared entirely. Unlimited food at the base of the chain. No predator capable of threatening adults. Millions of years of open ocean ahead. The blue whale, 30 meters long, the largest animal ever confirmed to have lived on this planet, did not exist while Megalodon was alive. It could not have. It required Megalodon's extinction before the conditions for its existence were even possible. That is the nature of apex predators. Their presence defines the ecosystem around them. But their absence defines it too, sometimes even more profoundly. Megalodon did not merely inhabit its ocean. It was the force that held the ocean's upper limits in place. And somewhere on the seafloor right now, one of its teeth is resting in the sediment. The last trace of the animal that once set the boundaries for everything else. Waiting still to be found.